So I'm standing in for Lorenzo to introduce our first speaker today. This is Héctor Martínez Rodríguez, who comes to us from the University of Pittsburgh, where he is working with Carlos Padenas on modeling of type 1a supernova and their remnants. Formerly, he was an undergrad in Madrid, where he did both his undergrad and his master's degree, and he told me his institution, and I can only pronounce the first syllable at this point because it's, again, slipped my mind, which makes me very Complutense, which makes me worried about my faculty. Anyway, Héctor is here this week working with myself on modeling of sub-Chandrasekhar type 1a supernova. We're doing something that others of us did on core collapse supernova. And he is in D331 right now. And today he's going to tell us about high neutronization in supernova remnants. So, thank you.
Thank you for the nice introduction, Dan. So yes, I'm going to tell you about some high neutronization that we have observed in type 1a supernova remnants. This is an example of a supernova remnant with an exceptionally high neutron-rich content that I will discuss afterwards. So first, I'm going to talk about neutronization in type 1a supernovae. Then I'm going to discuss the X-ray modeling and the measurements in the supernova remnants. Later on, I'm going to show my results. And I will finish with some small appendix about the calcium to sulfur mass ratio in type 1a supernova models, as well as with conclusions and future directions of work. So first, what is the motivation for my work? The motivation is the type 1a supernova progenitor problem. This is an example of type 1a supernova exploding to type 1a supernovae are the thermonuclear explosions of white dwarf stars in binary systems. There are so far two proposed channels for type 1a supernovae. The first one is the single degenerate channel, where a white dwarf is accreting material from a close non-degenerate companion, whether main sequence, star, subgiant, red giant, supergiant. The other channel is called the double degenerate, where two white dwarfs are merging together in a spiral path. The problem is that neither of these channels is clearly favored by either theory observations, which is why we talk about the type 1a supernova progenitor problem. So how can we tackle this problem? How can we solve this riddle? There are several ways. The one I'm focusing on today, as well as in my thesis, is neutronization. We define a parameter called the neutron excess eta, which is a kind of neutron to proton ratio in the ejecta of type 1a supernovae. In principle, white dwarfs are mainly composed by carbon and oxygen, and therefore they should have a zero neutron excess. However, the neutron excess in type 1a supernovae is different than zero, and there are three main sources that contribute to this neutron-rich material. The first one is the chemical composition of the white dwarf before the explosion, which is the initial neon-22 content. We also have the chemical composition before the explosion, a process called carbon simmering in the single degenerate channel. And finally, also in the single degenerate channel, during the explosion, we have the neutron-rich nuclear statistical equilibrium burning regime. Let's go to the first one. The neon-22 production in type 1a supernovae in white dwarfs. Well, first, in stars powered by the CNO cycle with 0H main sequence masses roughly bigger than 1.3 solar masses, this reaction, natrium-14 grabbing a proton and becoming oxygen-15 plus a gamma ray, is the slowest step in the CNO cycle. This means that all the CNO elements are going to pile up onto natrium-14. Afterwards, during the AGB phase, there is going to be hydrostatic helium burning on the surface of the star. And then, following this reaction chain, natrium-14 is going to become neon-22. Why is neon-22 a primary source of neutrons before the white dwarf phase? Because, as you have noticed, neon-22, when compared to neon-20, which is the main neon isotope, has two extra neutrons. So again, this is going to be a baseline neutronization for every single white dwarf. It can be shown that there is a nice linear relation between the neutron excess of the white dwarf and the metallicity of its progenitor, found by Frank Times in 2003. However, this relation between eta and Z can be modified in the single DNA channel via carbon simmering. What is carbon simmering? In the single DNA channel, we have a white dwarf, which is accreted material from this close, non-degenerate companion. It is getting hotter, it is getting denser, it is approaching the Chandrasekhar mass limit. Eventually, the white dwarf will start to fuse carbon in its core via carbon plus carbon going to sodium-23 plus a proton, or carbon plus carbon going to neon-20 plus an alpha particle. Eventually, the heat from these reactions is going to overcome the neutrino cooling, which is present on the white dwarf. Once this happens, we call this process carbon simmering. The white dwarf is going to grow a convective core to try to get rid of this huge energy. This core is going to encompass most of the ejecta, roughly 1 solar mass. And this carbon simmering process is going to last during 1,000 or 10,000 years before the final runaway as a Taiwanese supernova, roughly at this central temperature. I was modeling carbon simmering in Taiwanese supernovae with MESA, which is a fabulous open source stellar evolution code. And I was getting that roughly for all the metallicities I consider, the contribution to simmering to the neutron excess was roughly 0.2 in units of solar metallicity. I can show you this plot. This is the metallicity of the progenitor in solar units on the x-axis. On the y-axis, we have the central neutron excess in this convective core of the white dwarf. In red, we have the contribution of simmering to the neutron excess found by Tony Pirro and Lars Beilstein in 2008. This yellow band is the contribution that I found with MESA last year. And in blue, we have the simple linear relation between the neutron excess and the metallicity for double degenerate systems with no carbon simmering. So what we can see in this plot is that if we wanted to distinguish between double degenerate and single degenerate, we should try to go for low metallicities. For example, in the Large Magellanic Cloud. Because if we consider a solar metallicity typical of the Milky Way, the difference between this blue line and the yellow shaded band is pretty small. Again, these were some theoretical models that I was doing of carbon simmering. And my goal is to compare these models with observations. This was carbon simmering. And what about the third source for a non-negligible neutron excess, non-zero neutron excess in Taiwanese supernovae? It is the neutron-rich nuclear statistical equilibrium burn regime. As you know, Taiwanese supernovae mainly contribute to the chemical enrichment of the universe via iron peak elements. And they produce these elements in 3 different burn regimes, which depend on the density and on the temperature of the material. For low densities, low temperatures, we talk about the explosive silicon burning regime. For slightly higher densities, temperatures, we have the nuclear statistical equilibrium, the n-NSE. And then in the cores of the white dwarfs in Taiwanese supernovae for the single degenerate, we're going to have mainly the neutron-rich nuclear statistic equilibrium, or n-NSE. And as I said, these are determined by the temperature and the density of the exploding white dwarf. In this plot, I am showing some MESA models for an accreting white dwarf in the single DNA channel. This is log T in Kelvin, this is log rho in grams per centimeter cube, and these are some white dwarf masses, 0.7, 0.85, 1 solar mass, and this is a Chandrasekhar mass white dwarf. What you can see here is that the n-NSE burning densities, which are roughly above 10 to the 8, they require a Chandrasekhar mass progenitor, right? The higher the density, the more weak reactions, the more electron capture reactions will increase the neutron-rich material inside of the white dwarf. By neutron-rich material, I mean that usually Taiwanese supernovae produce nickel-56. However, in this n-NSE regime, at these high densities, these electron capture reactions are going to shift the equilibrium point from nickel-56 to neutronized isotopes, like, for example, manganese-55, nickel-58, and all of these are going to contribute to the final neutron excess of the supernova progenitor. But how can we measure this neutron excess in Taiwanese supernovae? Well, we can look at the structure which is left after the supernova explosion, which is called a supernova remnant. This is the archetypal picture of Tycho, a beautiful supernova remnant. And this is colored depending on the temperature for the X-ray emission. It is good to look at supernova remnants because we have Suzaku and Chandra archival data of this. I always like to show this plot when I am discussing supernova remnants. This is a plot by Hiroya Yamaguchi in 2014. This is the luminosity of the iron K alpha line in supernova remnants, and this is the centroid energy for the iron K alpha line. Inasmuch as supernova remnants expand, they are going to heat the surrounding medium to X-ray temperatures, so that if we look at that X-ray emission, we can see how the progenitor used to look like. We can see how the progenitor was regarding its composition. And this plot is showing that these in red are Taiwanese supernova remnants, whereas in blue we have core collapse supernova remnants. These color contours are some Chandrasekhar mass models for Taiwanese supernovae, and there is a nice distinction between Taiwanese supernovae and core collapse supernovae based on the iron centroid for the K-alpha transition. This occurs, core collapse supernovae have a more ionized ejecta because they have a stronger interaction with the circumstellar material, because core collapse supernovae leave a pre-supernova wind which interacts with the posterior shock in the remnant. That is why, again, we can distinguish, based on this iron centroid, between Taiwanese supernova and core collapse supernova remnants. Finally, these are dim supernova remnants, whereas here we have bright supernova remnants. I will go back to this plot afterwards because it is an important distinction as well. Well, regarding these X-ray spectra supernova remnants, this is the Suzaku spectrum of Tycho between 1.5 and 9 kiloelectron volts. Here we can see the transitions for the intermediate mass elements like silicon, sulfur, argon, calcium, whereas in here we have the transitions corresponding to the iron peak elements, the iron K-alpha transition. This little bump is chromium. This smaller bump is manganese. This is the iron K-beta line. So in principle, to prove the n-NSE burn regime in Taiwanese supernovae, we should look at manganese and chromium or nickel. However, the problem is that, as you can see, these lines are in general too weak. And this is a really good spectrum of a Taiwanese supernova remnant. In general, the signal-to-noise ratio is going to be pretty small, so it is going to be pretty difficult for us to detect n-NSE contribution in supernova remnants. So instead, we can look at the lines from these intermediate mass elements like sulfur, argon, or calcium, because they are going to be, in general, much brighter than manganese or chromium. This was the new idea we had for this project. Why are these important? Because, as argued by De et al. 2014, the calcium to sulfur mass ratio is an excellent tracer of neutronization in Taiwanese supernovae. It follows roughly a linear relation with the neutron excess. And the higher the neutron excess, the lower the calcium to sulfur mass ratio is going to be. So again, if we measure these abundances in the spectra of Taiwanese supernova remnants, if we model these spectra with the software expect, we have a way to detect neutronization. Aside from being brighter, why are these lines more adequate to detect neutronization? This is a picture of a 3D simulation of an exploding Taiwanese supernova. calcium to sulfur mass ratio is going to be important because calcium and sulfur are going to be produced in the outer layers of the exploding white dwarf, whereas on the inside of the white dwarf, we're going to have the iron peak elements. Consequently, calcium and sulfur are going to have no n-NSE contamination. So we have a clean neutron excess coming from neon-22 and additionally carbon simmering. So we can disentangle the n-NSE burn regime, and thus we have a nice way, a feasible way to detect neutronization in the single denary channel. So what about the X-ray modeling? I downloaded all those X-ray spectra of the type 1a supernova remnants, and I was using the software XSpec. The procedure XSpec follows is that you can make a chi-square fit with a certain model to the spectrum to try to find abundances, electron temperature, and the ionization timescale of the supernova remnant. You can take two different approaches, either a phenomenological Gaussian fit or different fits with models that XSpec already has. What is the problem with Gaussian fits in XSpec? In principle, you can take all those transitions for the intermediate mass elements, fit them to Gaussian functions, but then if you want to determine abundances and thereby mass ratios, you need to know the atomic addivities as a function of the electron temperature and ionization time scale. And in principle, these are not calculated. However, by using these models that XSpec already has, the non-equilibrium ionization models or the plane parallel shock models, XSpec directly retrieves both the electron temperature, the ionization timescale, and the abundances. Borkowski et al. 2001 argued that plane parallel shock models are more adequate to describe young supernova remnants because, unlike these non-equilibrium ionization models, the plane parallel shock models assume a broader range of ionization timescales, whereas these models assume a single ionization timescale for the ejecta. Nonetheless, as a sanity check, I was fitting my spectra with both these and these models, and the final mass ratios were roughly the same, which makes me feel confident that the modeling was pretty accurate. What about previous measurements in these X-ray spectral supernova remnants? Here I am showing mainly 3C397 by Hiroya in 2015 and collaborators. This supernova remnant has an extremely neutron-rich content. This is its spectrum around the iron K alpha transition. This is iron, manganese, chromium, and this huge bump is nickel. Why is this neutron-rich content? In type 1a supernovae, nickel 56 is going to decay to cobalt, and then it's going to decay to iron. So if we can see nickel after hundreds of years after the supernova exploded, this means that this nickel is going to be nickel 58 coming from the n-NSE burn regime. This is going to be stable nickel because the rest of the nickel will have decayed into iron 56. And the funny thing about this supernova remnant is that if you, in principle, neglect carbon simmering, if you focus on models with n-NSE contribution and neon-22, this supernova remnant is compatible with metallicities of 5 in solar units. And of course, we know that these stars don't exist in the Milky Way. These metallicities are extremely huge. And this is the plot. Here you can see manganese to iron. This is the nickel to iron mass ratio. And indeed, this supernova remnant is compatible with 5.4 models in solar units, which again is huge. Whereas Tycho and Kepler are compatible with 1.5, 1.8 models in solar metallicity, which is more normal for the Milky Way. So maybe for 3C397, it could have been a superchandra explosion. Maybe we don't understand carbon simmering. Maybe there is an additional source of neutronization. We don't know. So now regarding my results, in the plot I showed before with all the core collapse and type 1a supernova remnants, there were 11 type 1a supernova remnants. However, when I was trying to feed the spectra to measure accurate calcium to sulfur mass ratios, I could only stick to 5 supernova remnants, because for the other ones, the error bars were too broad. And here I am showing 3C397, N103b, D337, Kepler, and Tycho. These are the intermediate mass elements transitions, and these are decreased or sorted in decreasing ionization timescale. These for 3C397, D337, Kepler, and Tycho are galactic supernova remnants, whereas N103b is in the LMC. Again, these are my 5 supernova remnants. These are going to be my results for the calcium to sulfur mass ratio that I determined. Here, in this plot, I'm showing calcium to sulfur on the x-axis, and on the y-axis, I'm showing the chromium to iron mass ratio. Unfortunately for G337, I was unable to determine the chromium to iron because the signal to noise was too low, so I could only measure a calcium to sulfur mass ratio. This is the central value for G337, and these are the corresponding error bars. In this plot, if we forget about supernova nucleosynthesis models, here I'm just showing the final data. It is striking because if we expected only neon-22 to be the source of neutronization in these remnants, for N103b, in the Large Magellanic Cloud, this supernova remnant calcium to sulfur mass ratio should be around here, because as I said, the higher calcium to sulfur, the lower the neutronization. Thus, for metallicities typical of the LMC, this supernova remnant should be more to the right. And however, we can see in this plot that it is mingled with the Milky Way supernova remnants. Then, this is telling us that there has to be something else aside from the neon-22 neutronization in type 1a supernovae, because otherwise, yeah, this measurement should be around here, but instead it is comparable to Tycho and Kepler. Now, if we take these measurements and we use supernova nucleosynthesis models, by remembering that, for example, N103b and 3C397 are bright supernovae, whereas G337, Tycho, and Kepler are roughly dim supernovae, we have this. This is, again, calcium to sulfur. This is chromium to iron. These are models for Chandrasekhar mass, white dwarf, delayed detonation models. DDTA are bright supernova models. DDTF are dim supernova models. And here we can see that as Yamaguchi et al. Deduced for 3C397 using the iron peak elements, 3C397 is compatible with 5.4 solar metallicity models. So both the iron peak and the intermediate mass elements yield the same result for 3C397. I wanted to make the distinction between bright and dim supernovae because, for example, for 3C397, which was a bright supernova, these models, these dim supernovae, based on this plot, can be discarded. For N103b, the argument is the same. These dim models can be discarded. So its progenitor is compatible with roughly 1.8 solar metallicities. In Tycho, 1.8 as well, Kepler between 1.8 or 0.7. For sub-Chandrasekhar models, the final result is pretty much the same. For 3C397, as Yamaguchi et al. Inferred, it is not compatible in principle with sub-Chandra models. And 103b is again compatible with 1.8 solar metallicities like Tycho, Kepler between 1.8 and 0.7. And as you have noticed in both plots, G337 is compatible with dim models with an extremely high metallicity, like 3C397. So, this is just a summary. These two remnants are compatible with an extremely high metallicity progenitor. For N103b in the Large Magellanic Cloud, this metallicity is also high. So what we can do, and what we did, is that we compared these inferred metallicities with the local metallicity distribution functions for both the Milky Way and the LMC. So based on my models, I was interpolating within the model grids for the DDT and the subchannel models, and this is what I got. Here, I am showing the galactocentric distance for the Milky Way. So this is the center of the Milky Way. This is us, the solar system, at 8.3 kiloparsecs. These are the MDFs for the Milky Way. These are apogee data for the Milky Way, whereas this is the metallicity distribution function for the LMC adapted from another paper. And these are the values that I inferred based on the previous plots, where I was comparing my data with the models. What you can see, these are the percentiles. So this is the median for the MDF for each being in galactocentric distance. Kepler is roughly compatible with the local MDF. Tycho is a 2 sigma outlier, which is acceptable. However, D337 and C397 are clear outliers in their environments. The same happens for N103b in the LMC. This is the 2 sigma percentile, the 90th percentile, and this is the metallicity for N103b that I was inferring with my data and my models. So we have a sample of 5 objects, and 3 of them are clear outliers. Of course, you can wonder, should I trust the nucleosynthesis in your models? I am not proving the models to be correct. However, both these models, which I was using for the intermediate mass elements, these results agree with the same models and the iron peak elements. My results agree with Yamaguchi et al.'s results based on the iron peak. So both calcium to sulfur mass ratio and iron peak mass ratios yield the same neutronization for the supernova remnants, which makes us feel confident that the models reproduce to a fairly amount the neutronization in these supernova remnants. I have to say that we found some problems when we were studying the calcium to sulfur mass ratio because of this reaction rate of carbon plus oxygen. We were comparing our models to the models by Brockton-Miles, and we saw that this reaction rate has huge uncertainties because of the extrapolation of the S factor to the stellar regime when trying to determine the reaction rate. And the problem is that the calcium to sulfur mass ratio is going to be proportional to the abundance of alpha particles squared, and this value depends on this reaction rate. Because of the uncertainties I'm mentioning, the reaction was fully suppressed in our models. However, as I'm going to show now, the iron peak elements are largely unaffected by the value of this reaction rate. This is a plot for the several elements from hydrogen to zinc, and this is a comparison between the final mass ratios when the reaction is not included and when the reaction is fully included. As you can see, whether the reaction is included off or included on, the final difference in mass between manganese, chromium, iron, nickel, these are going to be largely unaffected by the value of this reaction rate. So manganese, chromium, iron, nickel, compare one case to the other, they're going to be pretty much the same. However, sulfur and calcium are largely affected by the value of this reaction rate. So this is a problem in supernova nucleosynthesis models. And of course, you can search in the literature for more models, and this means that you're opening Pandora's box. These are Chandrasekhar mass models. These are sub-Chandrasekhar mass models. And in this plot, I'm showing that most of the supernova models in the literature don't yield calcium to sulfur values which agree with my observations. However, these sub-Chandrasekhar mass models do, because they assume a helium layer on the surface which is going to detonate, and thus it's going to increase the alpha particles and increase the calcium to sulfur mass ratio. But again, in general, most of the models in the literature predict a calcium to sulfur mass ratio which is too low to explain observations. So this is a problem. So to summarize my talk, we have measured neutronization in supernova remnants, and we have found that for a supernova remnant in the LMC, its neutronization is comparable to supernova remnants in the Milky Way. So this is suggesting that there has to be something else aside from progenitor metallicity contributing to supernovae. Additionally, we have reproduced the same results with intermediate mass elements than the ones which were reproduced with iron peak elements for Tycho, Kepler, and 3C307. Also, for three supernova remnants, 3C307, G337, and N103b, when compared to the local MDFs, their metallicities are too high to be explained only by neon 22. So this is observational evidence for high neutronization in these three remnants. The problem is that if I want to explain the neutronization in these remnants with my simmering models, there is no way I can do so because my simmering contribution to Taiwanese supernovae was too low. So as ongoing work, there are some different simmering models this year that were predicting a higher increase in the neutron excess. Maybe there is the answer. Maybe there is something else aside from carbon simmering, neon 22, and n-NSE contributing to nucleosynthesis and to neutronization in Taiwanese supernovae. Additionally, we, as I stressed out, we want to determine the value of this reaction rate because it is extremely relevant for nucleosynthesis in Taiwanese supernovae, for redrift transfer, for the chemical enrichment of the universe. And finally, I want to stress out that future X-ray missions like the replacement for Astro H, these have the potential to constrain the values for the neutronization of my supernova remnants. Because with these future missions, I could easily detect neutronization coming from the iron peak elements. I would have a high resolution to measure abundances coming from manganese, chromium, and nickel. So we can really do good science with these supernova remnants in Taiwanese supernovae. And this was all. Thank you so much for your time.
Questions or comments? Please.
I found your talk very scary. When I looked at the isotope ratios that you were finding.
Which slide?
Basically, the last several.
Oh, the models. You mean?
Well, when you showed the results of calculations, and as here, the ion ratios in these models often were differing by a factor of 2.
Yes.
And these are supposed to be standard candles. Is it reasonable to suspect that all of these supernovae have the same intrinsic brightness at peak maximum when the neutronization process is so different or produces such different results? How can they be standard candles?
Well, I mean, the main brightness from Taiwanese supernovae is coming from nickel going to iron, and that process is not affected by this reaction rate, as I showed here. Like the brightness from supernovae are powered by nickel 56 decaying into cobalt 56 and then decaying into iron. So this should not affect the supernova brightness. These calcium and sulfur are produced on the surface and they don't power Taiwanese supernovae. But it is true, as you say, that most of these models are off by roughly a factor of 2. Also, I should say that all these models that agree with my observations are 1D models, whereas these models are all 3D or 2D models. So there has to be something else aside from this reaction rate. Perhaps multidimensional models cannot reproduce Taiwanese supernovae as well, because also these 1D models can use a full nucleosynthetical calculation. Whereas 3D models, it would be so computationally expensive that usually these employ a simplified nucleosynthetical reaction network. So the nucleosynthesis coming from these models is not going to be as accurate because, again, it will be computationally expensive. But yes, this will not affect the standard brightness of Taiwanese supernovae. This is only nucleosynthesis occurring in the outer layers of the supernovae.
Thank you. I found this reply reassuring.
Yeah, this affects the outer layers. Again, these guys don't really care whether the reaction rate is fully suppressed or fully included in the models. It is mainly these intermediate mass elements. But yes, we really want to tackle this problem. We want to use my observations and our models to try to determine a kind of effective attenuation factor for that reaction rate, for example.
Real quickly, what are the densities where the carbon-12, oxygen-16 burning is going on in the white dwarf? That's an important reaction in massive stars as well.
The densities I don't recall. I recall the temperatures. Like sulfur is synthesized at 2 gigakelvins and calcium is synthesized at 4 gigakelvins.
One last question, comment? If not, let's thank Héctor again.
Thank you.
We have another speaker. Don't go away.
Oh yeah, definitely.
Sit down.
Gdzie to mam sobie?
Gdzieś tak włóż, żeby ci nie...
Się to kieszeni zmieści.
To musisz przybrać tego. Right, Bozena is getting ready. So we are lucky to have Bozena Czerny visiting here this week. Bozena is known to a lot of people here. She visited several times here, but for postdocs and students, maybe this is the first time when we have a chance to hear her talk. Bozena studied in Warsaw, and she was a student and worked with Professor Martínez. She worked in theory of accretion disks and black holes, and not only. Then going to quasars, quasar structures, and the properties of the matter around the black holes. Bozena is also editor of the update now, so some of you probably got the inquiries to get the referee report for some of the papers. So there it is, Bozena, and she will talk about one of important new avenues, I guess, in looking into quasars.
Thank you. So it's nice to be again. My title of the talk is so long because I was not sure that anybody will come to my lecture because there are so many lectures around. So I preferred to contain everything in the title in case you will miss it. And I think that this problem of spectropolarimetry and the use of spectropolarimetry is important, although it's not really new. But okay, let's start with motivation. Yeah, you don't like this picture, but this is something which always has to be shown, even with the purpose of showing that it's wrong. So black hole mass measurements, it's really important, and I don't think I have to argue a lot for that because it's important for statistical studies, cosmology, whatever. And most popular methods are based on the line width and the line and the luminosity. And that kind of relies on the assumption that the broadline region is spherical, and actually here we see kind of spherical broadline region, while in reality the broadline region is not spherically symmetric, and it's mostly rotationally dominated. And what I tell you, it's not really news. Again, I think it's sometimes interesting to read the literature. This is one of the first papers, perhaps calling attention to the fact that the line width, h beta, depends somehow on the viewing angle. Here it is done using radio load sources. So the radio loudness correlates with the line width as Beverly Wills showed already, you see, many, many years ago. The viewing angle really still has some surprises. This is a surprise which I'm now working on with one of my students. Namely, we took a sample of sources with measured inclination angles. Those are radiolode quasars with large radio structure, so you measure the viewing angle from the radio structure. And in the case of this particular quasar, formal determination of the viewing angle is 89 degrees, which means you see it along the equatorial plane. Okay, let's say plus minus 10 degrees, but nevertheless. And what you see here in the shape of the magnesium line, magnesium 2 line, the line is not that broad, it's pretty normal, and then it's not double peak. So this viewing angle is a very complicated issue. And then one more motivation, it is still introduction. As I mentioned, the measurement of the black hole mass is usually based on the relation between the distance to the broadline region and line width and the luminosity. And so from the reverberation mapping, we have observational, you see a lot of green points, a relation between the monochromatic flux and the time delay or the size of the broadline region. And those kind of points well aligned along the certain best fit. I was always puzzled why this alignment is, this correlation is with monochromatic flux and not with bolometric luminosity, which would be much more intuitive. At least it was to me from the beginning. So we developed with my student a couple of years ago a model which is based on the fact that actually it's easy to push out the material from the disk when you have the dust in the disk atmosphere. So as soon as the temperature of the disk falls below the sublimation, dust sublimation temperature, you can get out some material from the disk easily. As you know, for example, winds in the case of dusty stars are much more powerful than in other cases. And this kind of a model fits nicely the observational data. Here I used two values of the dust temperature, 800 and 1500. The best fit actually is for 900 kelvins. But this is not the point of this seminar. The point of the seminar are outliers, which are here below this. And my Chinese collaborators are doing monitoring of sources which are below all those relations. By the way, those theoretical lines represent various masses, accretion rates, whatever you want. It does not depend on anything. So they do reverberation mapping, or at least a measurement delay for those outliers using Li-Jiang telescope, 2.4 meters, but that's good enough. And because the line width for all those sources are very narrow, they determined the Eddington ratio in those sources as to be very, very high, 10 or something like that. And now they develop a new model for the broadline region, taking into account that in highly super Eddington sources, you have something like a funnel, and then radiation is beamed, and then you do not irradiate the material which usually should be responsible for the broadline region, etc. That's fine. But I started to worry, what if we have a problem with this viewing angle? Because if we happen to see the source predominantly in Keplerian motion just face on, we will have a very narrow line, and then we will claim it's highly super Eddington, while in reality it's not. So I tried to look at some ways to test this, and then I found the paper by Viktor Afanasyev, 2015, where he actually did spectropolarimetric study of a type 1 object, and at the base of the study he could say a lot more about the broadline region and the structure, and he also noticed in one of his papers that the line in the polarized light is much broader than the line in unpolarized light. So looking at his papers, I realized that, well, the problem is not really new. Everything was done actually in the papers by Smith more than 10 years ago, all theory and a couple of observations, mostly theory. So the method is there, and we can try to use this method to see whether in polarized light we will see if we have a problem with the viewing angle. So here you have two more pictures from the paper by Smith et al., because, well, everything was done there. He introduced equatorial and polar scatterers, and in particular, equatorial scatterers are very important, because if you have a Keplerian motion and you see it face on, you do not see this motion. But if you have scatterers located in the same plane as this Keplerian motion, then scatterers see the whole range of velocities. And then the scattered and polarized emission can inform you what happened, what is the original width of the line which should be used in mass determination. So, for example, here in this picture you see that in total flux you see a line like this, but in polarized flux, this is model, you see double peak and significantly broader line. So the method is there. Actually, if you measure the polarization angle from the amplitude, you even can get the location of the scatterer. So there is a lot of information there, so why not to use this method? So we applied for observing time at this point, and shortly after we wrote a proposal, we saw that actually there is already a publication. It was published shortly after we submitted the proposal. It was really unfortunate because it would save us quite a lot of problems, I guess. So Baldi et al. Did exactly the same study we wanted to do for radiolode narrow line Seyfert 1 galaxy. And what they got, they have a very narrow emission line, H alpha, by the way, but in polarized light, they have something which is much broader. You see this kind of double peak pattern, much broader. So originally the source was narrow line Seyfert 1 galaxy, but when they measure full Wyckoff maximum here, they have 9,000. So the line is broader by a factor of 5, 6, in comparison with original determination. And then, of course, the mass is also by a factor of 5, 6 lower. And the source is in no means true narrow line Seyfert 1. It's just an impostor, right? But you can notice immediately that the level of polarization they detect at the maximum is 0.1%. While we were working, when applying for observing time, we were working based on the results of Smith that we expect something at a level of 1%. That's not so. Okay, anyway, we got this observing time, and then we got that amount of time we got based on this 1% polarization expected. So this well, a number of people were involved, including Viktor Afanasyev, who motivated us to do that, and my Chinese friends, and we got time to do a sample of objects. 3 of them were done with VLT telescope, and then 5 sources were done with LaCie NTT telescope, and this observation I did personally, my first observation ever done in my life, but I survived. NTT, of course, is service mode, so this is not a problem. So we got the data, and now we try to reduce that. And honestly, I have no results to show you because my student is still fighting with ISO software with no help, because nobody in Poland was using ISO software before, because we just joined ISO. And, so what we have for the moment is just very, very preliminary result. Only I'm showing it for one of the sources. So this is Markarian 1044, narrow line Seyfert 1 galaxy. The accretion rate or Eddington ratio is about 10 in this source, if we believe in Chinese determinations of everything. And the line is extremely narrow, 1,000 kilometers per second. So we think that perhaps there is some kind of a pattern here, but we have to work with the data still stronger. So there is even an attempt to subtract something and see the pattern. But if we believe in that pattern, then we are getting for the moment to high width. So because binning the data actually pushes things down, because you bin not the result, but you bin before you obtain the polarimetric measurement. So I think that if we do really proper reduction, we will have something like a detection for that source. I'm not sure about other things, because we calculated exposure time expecting 1%. Polarized flux, and I think we are getting something at the level of less than 0.2 already in this preliminary data. Then there is next problem. Here I show VLT results. VLT instrument is really perfect to do that, but as a second instrument we used NTT EFOSC2, and that was a mistake. We shouldn't do that. So if you do any polarization study, never ever use this instrument. Because to measure polarization, you need an instrument which is symmetric. So the light is going up and down, because this does not impose instrumental effects. But if you have third mirror, and then at some point you scatter your light at an angle of 45%, then whether the source is polarized or unpolarized, you get polarization for the 4%. So this is what we got. And now you have to fight really hard to get the proper result. Fortunately, we have 2 comparison stars, which were observed with NTT and this other instrument. And using them, I hope we will be able to get something. So for the moment, it's really very preliminary. But what I stress, for sure, this polarized fraction is below 0.2%. I think we will get something at a level of 0.1%. This is very low. So at the moment, I cannot tell you yet that I ruled this 10 Eddington ratio value for the source, but I think that in few weeks, when we go to Garching and try to do the reduction there, I will be able to tell you that. But I'm really puzzled by this low polarization. I am, honestly. So instead of the final summary, I would rather stress this fact that this polarization is surely so low. when you measure it in most, well, in typical sources. Why we should expect some polarization? There is this dusty torus there. So this torus is irradiated. It should do some kind of scattering. Then there is a lot of outflow, for example, in the form of UFO. I'm not sure how you pronounce UFO in UFO, whatever. Okay, ultra fast outflows. So those are, you see, highly polarized, highly ionized iron there. So you have a lot of material which is fully ionized, should do the scattering. Then there is another problem which I mentioned here, and which is also dates back to 80s. Namely, we know that the size of the accretion disk, if you measure it, either through microlensing or recently in Spitzer HST or whatever you want, and SWIFT campaign, this is always too small. I would think that if we have a lot of scattering, then part of the radiation actually comes scattered. And that could perhaps also explain why the size is always somewhat, well, by a factor of too large. I don't know. Anyway, I see a lot of reasons to have a lot of material which do scattering, and then I see this polarization at the level of 0.1%, which is too low in my opinion. So then I think perhaps the polarization is an issue. Maybe. But I do not have yet the explanation. So I just share my problem with you, and perhaps you have the solution to the problem. Okay, thank you.
Thank you, Bozena. Any questions?
No solution.
Do you have any idea of what the X-ray polarization might show in comparison to the optical polarization? Could you see the same kinds of effects with X-rays? You know, they're produced, of course, closer to the accretion disk, but should the polarization effects be similar?
Well, if you have scattering, you should have the same kind of polarization. But then if it is at the level of 0.1%, you will have a hard time to measure it, right?
We'll see in a few years.
Yes.
If the torus weren't as big or as dense as we think it is, would that have an effect resulting in less polarization?
Well, density is not a problem. It's only that if the physical size is small, so the intercepted fraction of the radiation is small, then of course you have no effect because you have no low chance to get radiation scattered. On the other hand, if you look at the infrared in many quasars, you see something like 30% of the radiation in the infrared component. So then the natural expectation is that 30% of your radiation got partially scattered, partially absorbed in this dusty torus. And the scattering and absorption is kind of comparable. That depends on the wavelength. So what happened? Why it's not there?
Oh, don't say that. This is very nice. So depolarization, so you have to have a constant depth of 1, and you can't have that if you see variability, rapid variability.
Yes, of course, we cannot have Compton. Yeah, but if you have some kind of clumpy medium which actually does the scattering, or then if you have strong Faraday rotation or strongly magnetized medium, that's probably the way how you can do it. But I don't have any estimates yet.